Right, welcome everybody. Welcome to the 11.3 user group meetings. We're going to be talking about new features in 11.3, which was released a couple of weeks ago. I'm going to do the bulk of the presentation. My name is David Heffernan. I'm in charge of software development at Anaconda, and we also have with us James Carlisle, Colin Lewis, and James Pell. Senior software developers who've worked on the developments we cover. Chris Heaton's listed on the slide there, but he's unable to join this particular session. If you're here tomorrow, then you'll definitely see Chris because he'll be presenting. Tomorrow, the webinar is new developments on wind turbine modeling and OrcaWave. So whilst this meeting is titled OrcaFlex new features, it's really OrcaFlex apart from wind turbine features. As I say, that will be presented at the same time, same times tomorrow. And if you want to come and see that presentation tomorrow on wind turbines and also OrcaWave, there's still time to register. If anybody has any questions on what we'll be presenting, then ask in the Zoom question and answer feature. My colleagues will deal with those one way or another. It may be that they answer in text in the question and answer feature, but they may also opt to mark the questions as answered live, in which case I will pick them up at the end of the presentation. Or if there are questions that I don't know the answer to, one of my colleagues will be able to do that. Right, let me switch over to OrcaFlex itself and just point out that although we're talking about, this presentation is for the new features in 11.3. We're not going to cover all the new functionality introduced in 11.3. There's more new functionality and changes than we have time to cover. And in fact, probably a lot of the features are maybe a little bit more minor, and they don't really merit being presented in this level of detail. However, if you want to know everything, all the gory details, all the new features, even the ones that we're not going to cover in this presentation, and you want to know more details about what we do present, then if you come to OrcaFlex, help, what's new, and everything's listed. Follow the hyperlinks and so on. I'm sure you all know how to use our help file by now. Okay, so we, as I say, we released 11.3 a couple of weeks ago. Some of you will have it already. Some of you won't have got it installed. So hopefully at the end of the presentation, you'll have a better idea of what's new. I'm going to start by talking about new functionality in lines, and the first sort of major development I will cover is tabular contents and expansion tables, which it's two features, two separate features, I suppose, but they're closely related, as we will see. And these features can be thought of mostly as improvements to existing functionality. There are actually some things that you could not do previously that you now can do. But quite a bit of the power of these new features is making it easier to build models and check that you've got your model working the way it should be working. And that's actually incredibly important. Being able to build models quickly and clearly does make a real difference. So let's start off by looking at slug flow which is an existing feature, or at least the slug flow contents. Don't use this program. Slug flow contents feature. Now, this feature is not new. This is really, I'm talking about this now because it's what is currently in the program, and we're going to look at that and understand that, and then try to see why we've introduced the new feature, which is actually the tabular contents that you can see below. And with slug flow, you can specify that the contents density varies along a line, and also you can specify the velocity, flow velocity. Here I just got a constant velocity 1 meter per second, but this can also be a time history. And the second part of this feature is for slug flow is the group specification, and you can here define what slugs are going to be in the line, the internal contents, how many slugs there are, distance between them, density, pattern, and so on. Now, this feature has been in the program for quite a number of years now. It's relatively powerful, but there's some things that you can't do with it, which I want to demonstrate. So if I just run a replay, speed it up a little bit, you can see on the 3D view the slugs that are defined in that pattern moving along the line. You can see range graphs here evolving with time, showing the bend moment that's caused by the additional weight force from the slug contents. And then the bottom right is the interesting one, I suppose, for at least for the message I want to get across, which is the contents density. So we've got multiple slugs within the line at any one time, but what you can see is that the pattern doesn't change, and the slugs go at the same speed. They can't catch up. They can't pass through each other. There's no mixing or separation, or any of the complex flow or multi-phase flow that can actually happen in a real riser. So that's what you can't do at the moment. One of the things that our new functionality is trying to offer. So obviously, one motivation for this is things like riser fatigue analysis, where slugging is a big factor. But as we'll see later on in a few minutes, this feature can also be used for stability analyses, lateral buckling, potentially upheaval buckling, pipeline walking, and maybe other things. So let's move on and look at what the new functionality is. And it is enabled by selecting the tabular option here in the content specification on the line data form. And when you do that, you are presented with a table full of the data that defines the contents. And again, just as you can for slug flow, this can vary with time and arc length. And in fact, these two columns are, you think of these as independent variables, and then the next 5 columns are the dependent variables. So each row says for the specified time and arc length, what is the density, temperature, pressure, mass flow rate, and flow velocity. And this allows you to specify really quite complex contents, behavior. You can have multi-phase contents. Typically, this data, if you're going to have something like that, some multi-phase contents description, it's going to come out of a separate flow assurance analysis, almost certainly using some other piece of software. You'll get the output of that software, process it in a form that can be input into OrcaFlex, and then push it into OrcaFlex, and then take things further. Now, I've talked about variation with time and arc length. It's possible to have, if you set all of the values to be n NA, then there's no variation with time, and likewise you can do the same thing with arc length. So usually you'll have variation with both time and arc length, but it is possible to have variation with just time and arc length. And also you might see these double quotes or dittos. These are a new feature that allow you to say the value in this cell is the same as the value above. And what we've actually done here is this data, we only actually specify and vary density and flow velocity. For temperature, pressure, and flow rate, it's 0 and then ditto all the way down. So whilst you can specify all of these columns, you don't have to. Another thing to say is, what happens at arc lengths and times that aren't specified? Well, in between the specified data, your values are interpolated. That interpolation is quite complex. There's some pitfalls that a naive interpolation might fall into. So the nuances behind that are covered in the documentation. Hopefully, the way we've implemented the interpolation, is designed to avoid the potential pitfalls. I'm not going to try and explain the technicalities behind those statements, but I will just refer you to the documentation, which has a lot more detail. Okay, so now let's move on and actually look at the simulation. If I run the replay, we can see the data as it happens. This is a graph of contents density. It's a range graph, so we can see how the contents density as a function of arc length evolves with time. And we see there's actually two slugs, one going faster than the other, catches up, passes through it. So it's sort of mimicking sort of mixing and separation potentially. So this isn't at all realistic. We don't have, we've not done any flow assurance or anything like that to come up with this. But this is just to illustrate that anyone who's used slug flow will know that you could never have done anything like this before. This is the sort of the full power of this new feature. Okay. And I would maybe also point out that the data here, it doesn't have to be consistent. So you could have here we've got a mass flow rate of 0, but a flow velocity that's non-zero. Well, that's not physically practical. That's just because we've made this data just to demonstrate the point. In reality, there's going to be some mass flow rate here as well, and almost certainly the temperature and pressure will be changing. So you don't necessarily have to have consistent data. So you might decide I'm just going to neglect the mass flow rate. I don't care about that for the analysis I'm doing. You might decide you don't care about the temperature and pressure variation or whatever. So that's just something to be aware of. You get to kind of pick and choose which bits of functionality are used. Density obviously feeds into weight and inertia. The flow velocity is really, that feeds into how things propagate. Mass flow rate is related to the centrifugal and Coriolis loading, and temperature and pressure. Well, we're going to come to those next, because the next feature to talk about is expansion tables. And those of you who've been looking at temperature and pressure, thinking, well, they're going to vary internally. In what particular way? I mean, temperature as a contents data has never been used in OrcaFlex before. So you might be wondering, how is that going to have an impact on the calculation? Well, that comes about from these new expansion tables. And expansion tables define a relationship between temperature, pressure, and expansion factor. So this is temperature and pressure of contents and expansion factor of the pipe. Now, in this data, again, the first two columns are independent variables. So expansion factor is a function of temperature and pressure. And in this particular model, with this data, we've actually chosen to say that we're only going to be interested in variation with temperature. So by marking pressure all as NA, we're effectively saying we're not going to be interested in variation of expansion factor with pressure. That's not going to factor into anything. But this can be like a 2D variation. And again, we use interpolation to come up with values for say temperature and pressure that aren't specified. This happens to be a linear relationship. The reason why we've got three rows specified is that we want expansion factor of 1 at temperature 20, but our temperature is going to vary between, I think it varies between 10 and 90 as it happens. And the expansion tables, you can define multiple expansion tables, and then line types refer to expansion tables. So every line type has associated with it an expansion table. It can have none if you don't want to model this. And this data, well, previously you could specify expansion factor as a time history per section. So you could model expansion and contraction previously, but you had to go and do a whole load of pre-processing to come up with time histories, and then you'd have to go and discretize the line accordingly, to allow different expansions at different points along the line. So it wasn't at all practical. Yes, you could model expansion and contraction, but it was a massive pain in the neck to do so. So the idea of this feature is to make it easier to build these models. If I look at the pipeline itself, the contents data, well, this also uses tabular contents, but there's no table specified. That's because we've elected that the data source be external. So how that is it's a text file. It's white space separated using columns in the same order as would be found in the table in the OrcaFlex GUI itself. That can be a bit of a fiddle to look at. So there's a nice preview option in OrcaFlex which shows it and puts in some column headers. So you can just make sure using this preview that your external file is interpreted correctly. And the external file, it can be very useful to have it as an external file, because for a start it can make working with the model easier, because if you have a huge amount of data, sometimes you can have millions of rows. It can be quite awkward to work with that when it's loaded in the model in reset state. But also it means you can share these files across multiple models, and that's quite often very, very useful when you're doing a series of restarts. Let's have a look at the rest of the model. Well, I'm going to put the model into static state, and I've got a pipeline on the seabed. If I look at the line type, the lateral friction coefficient is 0.5. I have these sleeper objects modeled using line supports. These are designed to initiate a buckle. So that's really where you have sleepers. Friction coefficient for the contact with the sleepers, the buckle initiators, is 0.2, so that's lower than the friction coefficient with the seabed. And I'll just also point out, we have also a lateral seabed resistance profile specified. So here we have a sort of a resistance buildup and a breakout. This is a feature added in 11.2. This resistance profile is applied hysteretically. Not a new feature to this version, but I just wanted to point out that there's a whole range of features that we've added that sort of used in concert to improve the modeling of this kind of system. So if I have a look at the replay, I've got a default workspace, and we're going to see, well, what happens when, again, I've got 4 range graphs, and we're going to run the replay and see how they evolve over time. Temperature, it's going to heat up a little bit at close to end A, and then the heat is gradually going to spread along the line towards NB. The expansion factor is going to kind of shadow the temperature. As the line heats up, it's going to heat up to like 90 degrees. As the line heats up, it expands and therefore goes into compression. So we will see the effective tension drop down. The line goes into compression, and where the line in the middle is over these sleepers, we're anticipating a lateral buckle, which we'll see the effect of that on this outer plane curvature graph. And also we will see it quite visually on the 3D view. So if I just advance the replay, we see it heating up, as I talked about. Speed the replay up a little bit. We heat up, and then the next part of the line heats up, and you can see the buckle. We can see the line's going into compression in the first part of the line. The heat sort of propagates down the line, and the second part of the line now goes into compression, and the sort of the buckle of the sleeper kind of grows even further. So that's exactly the kind of behavior we'd expect and anticipate. As I say, you could have modeled this before in OrcaFlex, but you'd have had to go and build a whole load of complicated expansion factor time histories, and you've had to discretize the line quite, in terms of sections, quite severely. It would have been a real pain to create this model. We could also have modeled this using static snapshots through restarts, because restarts will carry the friction history forward. And so these 2 features, tabular content, expansion factors, in combination with restarts and seabed resistance modeling, all of them sort of put together, make it much easier to perform these buckling, walking, stability analyses. We would not be surprised if there were further features in a sort of similar vein. I mentioned earlier upheaval buckling. Well, that you can kind of do to some degree at the moment, but the modeling is awkward. So I think we'll likely have to or want to put in some changes to the functionality to make it easier to do upheaval buckling and build the models. There may well be other things that users would like to see related to these features. Please do let us know your opinions and give us that feedback. Right, I will stop talking about contents and expansion and move on to truss structure modeling and free constraints. If I can find it. So I have a very simple example here that I'm going to use to introduce the topic, and hopefully the exposition will flow from there. I've modeled. I've got an isosceles triangle supported on a tether. On statics, it kind of hangs there. It's not very exciting. And I've got 3 lines, and at the end of each line, they're called BLT, which isn't actually named after a lunchtime sandwich. It's actually meant to signify going from bottom left to top, BRT bottom right to top, and BLBR bottom left to bottom right. And at the end of each of these things, we have constraints. So this line, the bottom line, it goes between bottom left and bottom right. And if you look at the data, yes, that's what it's connected to. And before I get into the sort of truss structure part, I'm actually going to talk about the constraints, because the constraints are quite interesting. The constraints, this is a new feature in 11.3. These constraints are connected to free, and that's not something that you could do before. And when they are connected to free, then the data form, a lot of the data disappears. You don't have any degrees of freedom. The in-frame and out-frame are combined. There's drawing data and tags, there's position data, and then there's applied loads. You can apply loads, but in this case, I've got none. So what is this object doing? It's really got no physical properties. It's not doing anything. It's just acting as kind of a node, a frame of reference, a way to connect other objects together. It allows me, if I were to move this object, then it allows me to move the objects that are connected to it. And if I were to, I can use it also to report loads. I can report all the loads summed at one point. So these kind of objects are quite useful. In previous versions of OrcaFlex, you would have used 60 boys with all the properties set to 0, which works fine, but 60 boys come with a lot of extra baggage, and you have to explicitly go and set the properties to 0. So we kind of took the advantage, took the opportunity to take constraints, allow them to have free connection, and make them really an object dedicated for this purpose of using as a frame of reference or a connector. The name is a little bit unfortunate. A free constraint. How can you constrain something that's free? It's kind of a contradiction in terms, but historically we had constraints. We connected them to nothing. Well, that's called free in OrcaFlex. So you end up, almost inevitably with this name, free constraint, which sounds a bit odd, but it is what it is. But anytime where you previously would have used a 60 boy with 0 properties, you're probably best off now using free constraint. Now, if I enable the end axes, we can see that we've set the end orientations correctly. If I look at each of the lines one by one, then they're all the Z direction is going from end A to end B. This line, the ends are 50 meters apart, so the section length has been set to 50 meters, and the declination set as you'd expect. If I look at one of the other lines, then this is one of the two bottom to top lines. Then, well, I had to do some Pythagoras to come up with this value, and I had to do some trigonometry to come up with the declination. And there's two lines like that. Now, it's not that hard to do trigonometry. If you have lots of lines, then it's a little bit of a pain, but it's not that big a deal. But it's an extra thing to do, when really what we actually want to do for a model like this, where you've got these sort of straight rigid braces or whatever, you really want to say, just let the lines unstressed state be basically a straight line between the two ends. So that's a feature that we've been thinking about for quite a while, and we've actually added in 11.3. Here's my version of the same model, but now the new feature is we can say that the length and end orientations are calculated from end positions. So now the length, grayed out, you can't edit it, it's calculated by the program. Likewise, the orientations. you know, these are the same numbers we saw before that I'd worked out myself by doing some trigonometry, but now the program is working them out. And just remember that value 32. The beauty of this is if I need to edit something and move something, I can edit my free constraints, bring it in, and we see the numbers have changed. Length has changed, and so on. So, you know, if you're building a big model like this, it's going to make a massive difference to your model building. One thing that you'll have seen is that we've got uniform segmentation. We've got a single section, uniform discretization. Well, what if you want to have varying discretization along the line? Well, yes, you can add multiple sections to achieve that, but how do you specify the section length? It's not editable, it's grayed out. Well, instead of specifying the length directly, you can specify a weighting. So here by setting the weighting of this middle section to 3, I'm saying I've got 3 sections, this totals up to 5, so 3/5 in the middle. I'm going to say it's a section length of 5, and the 1/5 either side have a section length of 1. So it's finer discretization at the ends. There you go. So you've got quite a lot of flexibility still. Now let's look at a more interesting model. Having done the simple model to get the concept across. This is a model of a jacket which we're going to launch off the back of this barge, and some poor sap has come along and, you know, calculated all of these values. I think there was a spreadsheet prepared to do this. I think actually the people that prepared the spreadsheet to calculate all this might actually be in the webinar with us. But building these models, it's not a lot of fun. Anytime you need to change anything, you know, it's quite arduous. You're going to end up with, you know, you've got loads of lines. You're going to end up pasting values out of Excel into here. And the statics works, but it takes quite a lot of effort to get it to work. I can't remember how many iterations it takes, but you can see it's kind of chugging along. It takes quite a lot more iterations to solve. I'm going to stop it there, and I'm going to move to the alternative way. And each of these lines now has been changed from having the length and end orientations being specified explicitly to having the length and end orientations calculated from the end positions. And when you do this, you'll also notice in the previous model, we had lots of sag in the lines in the reset state. Well, now OrcaFlex, because you've told it effectively, the unstressed state is going to be a straight line between the ends. OrcaFlex actually knows this and can draw it in reset state like this. And actually it uses this as the initial value for statics. So it looks cleaner while you're building the model. Even more when you come to do statics, it goes really quickly. So this was like, you know, banged straight in 6 iterations. Now, if I look at the, slow that down. I'm just gonna show the replay. Just because it's nice, it's a nice looking replay, and you know, I wanted to show off the capability of the software. Over the jacket slides down off the back of the barge, and the rockers tip it in nice and safely. So quite a nice model. Still quite hard and complicated to build, but a lot easier to build now than in previous times. Right, I will now move on to the last couple of minor features with lines. I'm going to talk about the code checks functionality, which has been in the program for quite some time, and specifically the DNV F101 code. This got updated and renamed in a 2021 edition of the code to ST F101. There's in OrcaFlex 11.3, we've made some changes to reflect the changes to the code itself. There's some new data items and results variables to reflect this. They're covered in the documentation. So if you want to know more about it, have a look at the documentation. The older DNV OS F101, the results variables for that, they're still supported. So if you're working to that older code, then you can still do so. And the final thing I'm going to talk about is almost, I mean, it's almost not even classed as a new feature, but I just want to draw your attention to a change so that you aren't caught out when you encounter it. Now, the lay azimuth data here, many of you will be familiar with a button appearing on the form here labeled set lay azimuth, and you would click that button and the lay azimuth would be modified to act in to give you the azimuth from the bottom end towards the top end. And that button's disappeared. And before anyone panics and freaks out, we've not taken the feature away. For consistency purposes with other functionality in the program, we've moved the feature to live on the context menu. So you right-click the data, click that, and then the lay azimuth is set for you. So I really wanted to mention this just to try and avoid you all wondering where it's gone and losing time looking for it, and also maybe to avoid lots of you sending us panicky emails asking why this feature has been removed. It hasn't been removed, it's just been implemented differently. Now, that's enough for lines. I will now talk about restarts. So restart analyses, these were added, the feature was added in 11.1. It was the big new functionality in version 11.1. And it was very, very comprehensive even in 11.1, but there were some aspects of the program that weren't enabled to work with restarts. So a restart analysis is an analysis where you begin, your initial state is taken from the state calculated by a prior or parent analysis. And one of the features that did not work alongside restart analyses was line feeding. And that's something we've changed in version 11.3. So now I'm going to look at, this is the end of the chain. If I look at the restart parents, then there's actually five models in the restart chain, a bunch of dynamics, and we're going to no payout. We're going to start doing some payout. We're going to ramp it up. We're going to have some constant velocity payout of the line. We're going to ramp it back down to 0, and then we're going to have a settle down phase. So if I look at the feeding data here, then this is the final. Remember, this is the final model in the chain as a payout rate of 0. If I go up and have a look at the previous one, which was stop payout, then it's a variable payout rate, and yeah, it's the payout rate ramps down from 0.5 to 0, and the next parent has a constant payout rate of 0.5. The next parent has a payout rate that goes from 0 to 0.5, and the final parent, the initial analysis, it's got 0 payout rate. So if I load the simulation here, what has happened here? No, there we go. Not quite sure what went on there. I think I've moved these files around, so that's what happened. Anyway, what we see with my graphs, these are actually collated results, time histories. We can see how the tension varies. The tension varies because as we pay out line, more line is on the seabed, less of it is, there's a lesser sort of supported distance, so the tension reduces accordingly, and you can see how the actual arc length varies. So this has clearly got some payout going on, but there's actually, although it runs from -20 to 80, this particular simulation only runs from 70 to 80. So what we have here are collated results, collated across the entire restart chain. And if I run a restarts replay, I'm going to sort of home in. This is the initial analysis where there's no payout, and you can see at the top nothing happening in terms of feeding. And then when we hit this point, it's 20 seconds. We start feeding out line through one restart after another, and eventually we stop. So that's really just to convince you that we now can do line feeding with restart analysis. Now, if we go back to when we initially introduced restarts, in the very first user group meetings around that time, a question that was asked repeatedly was, can you do a restart from a point in the middle of a simulation? And at that point, the answer was no. The restarts were only possible from the end of the parent analysis. But now in 11.3, you can restart from a specified time in the parent. And this option, we refer to this as a mid-simulation restart. Now, to perform a restart analysis, OrcaFlex has to restore the entire calculation state from that particular point, the chosen point of the parent analysis. And the state that gets restored, this calculation state that is restored to perform a restart, we call this the restart state. We store the restart state in the simulation file. And the restart state is large. There's a lot of it. It's a lot bigger than the amount of information required for a log sample. So the log is what's used to generate time history and range graph results. And the size of one log sample is a lot less than the size of a restart state. So it's something more than an order of magnitude. So if we were to automatically store the restart state for every log sample, then your simulation files would be like 10, 20, 30 times bigger. And you don't want that. You really don't want that. And your IT department, they also don't want that, because they're going to be left with these huge files that you'll be dumping onto their disks. So what do we do instead? Well, instead, we require that you specify the times at which restart state is recorded, captured, and stored. And you do that on the restart state page of the general data form. Now, we could have defined this data as just being a table with a list of each individual time which you want recorded, but we've tried to be a little bit more general and allow you some more power by letting you provide intervals, start and stop times, and then the time interval within that. So here, this allows you to say, I want to record between this time and this time at a particular interval, and so maybe you wanted to record all the values between a certain two times, it means you can specify it in a single row rather than having to like write them all out manually. So this data, the way it's interpreted, we're going to record between 0 and 10 at a 5-second interval. So we're going to get 0, 5, and 10. Let's look at the bottom one next. That's very similar. 2-second interval this time. We're going to get 50, 52, 54, but not 56 because 56 is beyond 55. So 50, 52, 54. The final one, we're going from 30 to 30. Well, we're just going to get a single value. And in fact, this interval doesn't matter in this case. And you can check that you're going to get the values that you expect by bringing up the properties report. And sure enough, these are those times. You know, that's the first row, that's the second row, that's the third row. Now, let's just try things a little bit differently. You can also use tilde to mean the start of the simulation. Tilde here means the end of the simulation. And if I put in an interval of 0, then in fact, if the interval is less than the log sample, then you will get restart recording sampled at the same interval same frequency as the log sample. So this is actually a way we're going to get what I said you didn't want to do, which is the restart state recorded to every single log interval. And if I look at that, then sure enough, all the way. Okay, my Zoom is freaking out. There we go, all the way down to 100. But also note that now my simulation file is a whopping 300 megabytes. What was it? What was it before? Well, with this data, it was 7 megabytes. So, yeah, that's a lot bigger, right? So you really don't want to be just indiscriminately logging or recording every single log interval, log sample. Right. Okay. So then the second bit of data here you might have spotted periodic recording. What this is really for is this records a number of samples at the end of the simulation. It's like a sort of rolling window, and we're going to record at a particular interval, and we're going to retain the number you specify here. So in this case, we're going to retain the last 5. But this can be any value. Count n can be any value. We will retain the last n, the value you specify here, sampled at the interval you specify here. And so the point about this is maybe your simulation goes unstable partway through. Maybe it's a very long simulation and you get 90% through and you don't want to have to rerun it all. So you restart from a value close to the end. You maybe reduce your time step and maybe it completes. And that's a quicker way of getting to the end. If I load up the simulation file, I can also, when I now look at the properties here, as well as getting these target restart recording times, you also get the actual restart recording time. So you can now see what values actually were recorded. The next thing to point about, we've talked all about how you choose what times to record the state at. How do you use that? How do you specify which time to restart from? Well, this is a restart model. And here you see the new data item. Here we say we want to restart. In this case, we're restarting from time 97 seconds. And because there's a simulation file present, OrcaFlex is able to sort of briefly look into that simulation file and present you a helpful hint telling you what times are available. So this model, if I run it, this model will succeed. we're able to run the simulation. And as it happens, I've released the line, I've dropped the time step, and we see what happens. Here's an example where you specify, I want to restart from 90 seconds. Well, if we look here, 90 seconds isn't in this list, so we wonder what's going to happen. Well, what happens is we get an error message telling us we cannot perform the restart because we didn't record state at that time. So, I mean, in an ideal world, it would be nice if you could just arbitrarily restart from anywhere without having to think ahead of time in your parent analysis to do that. But in reality, you probably don't want that because of, as I say, because of the time it takes. Right, a couple more things to talk about for restarts. I'm going to look at collated results, and this is the example we used to demonstrate restarts right back in 11.1. I'm just going to bring up a collated result, collated across all restart parents of the tension in the line at end A, and this particular model. If I just run a replay, okay. What happens in this replay is it's a series of the analysis we will have here is a long chain of static restarts. There's, you know, what is it, over 90 separate static analyses, one after the other. Friction history is carried forward through each restart, and what we're doing is we're dragging the end of the line through a circular arc from 0 to 90 degrees. And how have we got a time history for a series of static analyses? Well, what we actually did, again, if you look at the restart parent, is each of these static analyses has a nominal time specified. It's not real time as such, because there's no dynamics, it's a static analyses. I'm really just using time effectively just as a label along the x-axis of these graphs, and time maps directly to angle. So while we call it time histories, it's just a neat way of using the results that OrcaFlex provides to show how this value evolves through the chain of restarts. All of this is not new. This was all available in 11.1 in the GUI, but in the API, you weren't able to pull up these collated results. So we've seen these collated results earlier as well with line feeding, a very powerful feature, but you couldn't get them in the API. You had to load every single simulation file up one by one and sort of piece together all the results, which was a bit of a faff. So in 11.3 in the API, it's now possible to ask for collated sample times, collated time history. It's also possible for range graphs, for multiple time histories. So any of the results that you can work with for which collated results make sense. There's now collated versions of the standard results API functions. You know, it's pretty hopefully pretty straightforward, a lot easier than doing it all yourself. If I run this now, it'll take a little while because it has to load up all the simulation files, but we're gonna get a matplotlib plot in a second, and you know that is the same plot. Yeah, it's kind of the same plot out of the Python API as we got from the GUI. Right, the final thing to talk about that's sort of related to restarts, I'm not going to cover in any detail, but I'm just going to point at it and refer to the documentation. If you're working with time histories across a chain of restarts, then this functionality, the new time history import range, may be important. I have prepared some examples for this, but there's not space to fit them into this presentation. It's also quite an esoteric subject matter. So what I'm going to do instead is I will cover this in a separate news post. I'll possibly record a video to go with it. But look out for that in a separate post. And if you're using time histories with restart analyses, then this is going to be worth a bit of a read in the documentation. It's going to be relevant to you. The final thing I want to talk about in this meeting is Morison elements. Morison elements have been in the program since 10.2, so maybe, what is that, like about 5 years now. Morison elements are a collection of rigid cylinders which attract hydrodynamic loads. They can be connected to either to vessels or 60 buoys. The most typical usage is to connect them to vessels. You might use them to include quadratic viscous drag on, say, the bracing of a semi-sub, where that quadratic drag was neglected in your linear hydrodynamic analysis. That's the kind of application that they get used for. But because that was the initial focus, when we first released them, Morison elements would attract drag loads but no other loading. And over the years, we've had a number of requests that we also include added mass and fluid inertia for Morison elements, and we've done that in this release. So this is the data that we had before, where you specify the drag coefficient CD and the corresponding drag diameters. And the new functionality is in the second page. Here you specify again the hydrodynamic diameters, the added mass coefficient CA, the inertial coefficient CM. So very familiar from things like lines and spar buoys. There's really nothing much more to say about that, other than just to give a shout out to OrcaWave. This will be covered in tomorrow's webinar. But there's an analogous feature in OrcaWave, the OrcaWave Morison element, very, very similar. And to match OrcaFlex, we've extended that in OrcaWave in the same way. Okay, and the final thing I'm going to talk about is Python. And also some sort of notices about version support for Python and Windows. Now, Python is used widely with OrcaFlex. Embedded Python embedded Python in particular is growing lately. Embedded Python, this is where you have OrcaFlex hosts a Python interpreter, and then OrcaFlex calls into your Python code using the hosted embedded Python interpreter to execute your code using values, data and results typically from OrcaFlex. Your Python code does something with it and then feeds the values back into OrcaFlex. This is used by external functions, post-calculation actions, user-defined results, etc. And embedded Python has been part of OrcaFlex for many years now, but it's become more mainstream, particularly with the introduction of the turbine object, because turbine controllers usually require Python external functions, even when the controller is actually implemented in a DLL. There's usually a Python interface between OrcaFlex and the DLL that sits in between the brokers, the communication. So for a lot of models now, you need to have an embedded Python installed, but that previously has not been part of the OrcaFlex installation process. So you would install OrcaFlex, and then you have to go and separately install Python and any third-party modules that are needed. And that can be tricky sometimes. Sometimes if your machine's locked down in a corporate environment, you need to get IT to support it. And it was all a little bit awkward for some users. So starting from 11.3 in the install program, we now have the option of, when installing OrcaFlex, and this is a screenshot from the OrcaFlex installer, we now have the option of also installing an embedded Python that is sandboxed and private to OrcaFlex. You are able to extend it by adding extra modules if you need. So you know, that's quite useful, because there may be some particular modules that your code is using that we don't install. We install it with pip, NumPy, SymPy, PyYAML, and OrcaFlex API. But as I say, if you need to extend it to add more, you can do so. I think it's a 3.10 installation. You may already have Python installed. You may already have a well-developed process for getting Python onto your machines, and in that case, you quite possibly and maybe probably don't want to install the embedded Python, because if you choose to install the embedded Python, that will then be used by OrcaFlex. So you might find yourself just installing it without maybe thinking through the consequences, and suddenly you find that this version of Python is now being used by your external functions, and maybe or your other embedded Python code, and maybe doesn't have the required modules. So if you've already got a working setup and a process, and if embedded Python isn't an issue for you, then stick with what you've got, I would say, and don't bother installing our embedded Python. I would also note that the demo version installer now includes embedded Python 2, so it means you can do things like install the demo version and load our turbine examples immediately without having to go and install some separate Python installation set. Back to Python itself, we now have, I'm going to switch back into presentation mode. You can see if I wake up, yeah, we now have we've added type hints to the Python API, so that's helpful for you to understand what type is required. Helpful for some static analysis. So it's a useful thing to do, and any good Python IDE will show you the type hints. Unfortunately, we don't yet have a doc string. So this is Matplotlib, which does have doc strings, and you get the nice documentation in line. When you see this and see how nice it is to see information like this directly in your IDE, then I think it must be time for us to put the effort in and put doc strings into the API. Now, some final notices. Anaconda. I'm just going to stop the share at this point. Anaconda environments are now recognized by OrcaFlex. So if you start OrcaFlex from an Anaconda console, then OrcaFlex will use the active Anaconda environment. And this matches the functionality that already exists for venv and virtual env. Anaconda can be a bit of a moving target. And so we've experienced times when a new version of Anaconda has broken our interface with it, and we've had to adapt. I think our code's getting cleaner, and Anaconda is changing less rapidly, and Python itself is getting much more stable. So hopefully we won't have too much trouble keeping up with any changes in Anaconda. Now, a year ago, we announced that Python 2 will not be supported in version 11.3. Python 2 reached end of life at the start of 2020. And so as of 11.3, OrcaFlex now only supports Python 3.6 and later. Python 3.11 was very recently released, and OrcaFlex 11.3 supports Python 3.11. And also the latest minor upgrade to 11.2, which is 11.2e, that also supports Python 3.11. We announced earlier in the year on our website that OrcaFlex 11.3 will be the final release of OrcaFlex that supports Windows 8.1. Windows 8.1 reaches end of extended support in January. And so for future releases, it'll be Windows 10 and later. and 32-bit machines, so that's 32-bit versions of Windows. They will no longer be supported after 11.3. Microsoft haven't offered 32-bit versions of Windows 10 since around 2020. Windows 11 is only available for 64-bit systems. OrcaFlex and OrcaWave both really require 64-bit processors for efficient performance. We don't remember the last time we came across a user running on a 32-bit version of the operating system. So again, we announced this earlier in the year on our website. Version 11.3 will be the final version of OrcaFlex, which can be installed on a 32-bit version of Windows. It doesn't mean that you can't run 32-bit versions of OrcaFlex if you need to. So we will still be supplying both 32 and 64-bit versions of the program executables, the exe files and the DLL. And sometimes, almost always, because you're using an external function DLL that is only available as a 32-bit DLL, you get pushed into using the 32-bit version of the program. You can still do that on a 64-bit operating system. We would always recommend, where you can, to use a 64-bit versions of the executables. And we're making both of these changes, for Windows 8, for 32-bit machines. We're making those changes because we would have to test, and it's an extra step for us to test all this stuff, testing our installation package, and so on. And so limiting the testing we do allows us to make that testing better, and I believe, and allows us to spend more time concentrating on features. You probably don't want us testing on operating systems that nobody's using. What's the point of us doing that? Right, so that's I'm a little bit over my my intended hour, but I will stop talking, at least on the presentation side now, and see if there's any questions. So I suspect there's been a few questions answered by my colleagues. Is there an option to use time varying slug flow? I mean, I think that's what I demonstrated. The tabular contents allows that entire content specification to vary pretty much arbitrarily with both time and arc length. So to be honest, I'm not quite sure I understand that question directly. So if my answer hasn't really got at what you were asking, then maybe send us an email with a more detailed follow-up. What are the default values for the restart state times? Is the final instant the default restart option? I mean, I guess, when you create a new, let me just do this. In fact, I'm actually doing something on my screen that you can't see, so let me just share my screen again. I'm just going to save a model. If I create a restart analysis from that parent, then the default restart from time is tilde, and that means the end of the parent. So the default is the same behavior as we had previously. You also ask, does this change the syntax in the YAML files? Yes, it does. I mean, inevitably, there's some extra data, so obviously that data wasn't present. But if you aren't, yeah, that's normal, and we don't actually ever strive to keep the YAML format forwards and backwards compatible in the same way we do with the binary format. So yes, there will be some changes in the text data file format because of that. Okay, then the final question. says Python code for the collate example does not show file names to collate. Does it grab all the files in the working directory? Well, that's a good question. I've again, for this example, I've just given you the most basic. But if I look at, if I can persuade my ID to bring up the type hints, then the final parameter here, restart models, allows you to specify which files in the restart chain are to be included. So, I mean, it would never grab all the files in the working directory. It would only ever, I mean, if you omit this, it grabs all of it takes all the files up the parent chain. But if you only want to include a subset of those files in the parent chain, then you can do so. I hope that answers your question. Right. I don't see. I'm going to have a look at the answered question, see if there's any. Yeah, I think they've all been answered fine. If you do have any more questions, anybody who's still with us, I can see that we still have quite a few people who've managed to survive over an hour of me talking, which is a very impressive performance on your behalf. And you know, thanks a lot for attending. If you have any more questions, now's a chance to do it. If you pop those in the question and answer, and you managed to do that before we've wrapped up, then we will answer them. Everyone who's attended will receive an email with a link to a feedback form. So if you it would really appreciate it if you could provide us that feedback. It's very valuable. We use it to guide future developments. I'd hope that you can see from the features that are going into the program that the feedback that is offered is taken into account. If you're attending the webinar tomorrow on turbines and OrcaWave, then please just send one feedback form. So maybe wait until you've done that webinar tomorrow and then send the feedback in. The recordings of the webinars will appear on the website in I'm not quite sure, it'll take a little while to get them prepared. If any of your colleagues haven't been able to attend, then look out for these recordings and they'll be able to watch them. Or if you want to go back and revisit something that I said that you want to hear again, you can do so. Alternatively, the webinars will be available as on-demand webinars. So your colleagues can sign up and watch the recordings using the same Zoom links that you used to sign up. That's on our website. There's a question that's just appeared. It says, could you confirm that older version restart simulation files could not be collated? I mean, that's not true. The collation, results collation was available from 11.1. What is new in 11.3 is that this collation can be done through the API. Previously, you had to do it manually. I hope I've understood that that question. Right, I think we'll wrap it up there. I suspect that's. Oh, there's another question. Oh, I've got to thank you. Right, we're going to wrap it up there. I think that's probably all the questions now. Thanks a lot for attending. I hope you found it useful. If you have any follow-up questions, then email us in the usual way. We look forward to your feedback forms in due course, and we hope to see some of you again tomorrow for the turbines and OrcaWave session. Okay, thanks a lot, everybody, and goodbye.